This is the video for 1, 3 real numbers. A square root is a number which produces a specified quantity when multiplied by itself. So for example, 3 is the square root of 9 because 3 squared equals 9. The radical symbol houses the radicand, and I drew a picture there of the radical symbol. The radicand is what's under the radical symbol. So if I was to actually draw out the square root of 9, the 9 is the radicand. A perfect square is the product of a rational number multiplied by itself. So 3 squared equals 9, so 9 is a perfect square. A set is a well-defined collection of objects, and the element of a set is the object used to form a set. A subset is a set within a set. So in my example, the set is algebra students. The elements of the set are Bob, Dan, Pam, and Mary, and the subsets are boys and girls. And finally, an inequality is the relation between two expressions that are not equal. So for example, if I said 2 is less than 4, that would be an inequality. Okay, example number 1, simplifying square root expressions. The square root of 81 is 9 because 9 squared is 81. The square root of 9 over 16 is the same thing as saying the square root of 9 over the square root of 16, which is 3 over 4. Do not convert 9 over 16 into a decimal. If the problem gives you a fraction, you need to know how to produce the answer as a fraction. So go ahead and hit pause and work on your own problems. And here are the answers. Again, remember the square root of 81 over 121 is the same thing as saying the square root of 81 over the square root of 121. Example number 2, estimating a square root. You need to memorize up through 13 squared, which is 169. But if you go over that, it's reasonable to use your calculator. So if you're given the square root of 386, you can go ahead and use your calculator and you find that the square root of 386 is approximately 19.6. So then you can go ahead and estimate that and say the square root of 386 is approximately 20. And those squiggly lines mean approximately. So do the on your own and don't use a calculator. On this one, you can say that the square root of 34 is approximately 6 because the square root of 36 is 6. Your other perfect squares are going to be the square root of 25 and the square root of 49, but your closest one is going to be the square root of 36, which is 6. So you can say the square root of 34 is approximately 6. Example number 3, classifying real numbers. I gave you a handout. Here's the handout that you have to memorize, and this is the set of all real numbers. And the reason why we have to specify real numbers is because there is this other set of numbers called imaginary numbers. And we will not talk about imaginary numbers until Algebra 2, but you do need to know there is another set called imaginary, which is why we need to specify real numbers. So the two major subsets of real numbers are rational and irrational numbers. Rational and irrational numbers are both subsets of real numbers, and the main difference between the two is rational numbers are any number that can be put into the form of a fraction. Irrational numbers cannot. Let me repeat that because that's super important. Rational numbers can be put into the form of a fraction, and irrational numbers cannot. So notice here we have a terminating decimal. Terminating decimals can be put into the form of a fraction, and so can repeating decimals. Repeating decimals can be put into the form of a fraction, but you haven't learned how to do that yet, and you probably will not until pre-cal. But repeating decimals can be put into the form of a fraction, and so rational numbers are any number that can be put into the form of a fraction, and irrational numbers cannot be. Now, you do have these other subsets of rational numbers that you do need to memorize. So down here we have natural numbers, which are also known as our counting numbers. And the reason why they're called counting numbers is because this is how we learn how to count when we are young children. When we're learning how to count, we start at 1, 2, 3. We don't start at 0. When you're counting eggs in a basket, for example, you start at 1. You go 1, 2, 3. You don't start at 0. So your natural numbers are your counting numbers. Your whole numbers are your natural numbers plus 0. And the way I remember that 0 is a whole number is 0 looks a lot like the O in the word whole. And that's how I remember 0 is a whole number but not a natural number. Your integers are your whole numbers and their opposites. And so those are the subsets of rational numbers. And this is how I think of it. Let's pretend that's the Milky Way galaxy. This is Earth, and this is Mars. Mars and Earth are both in the Milky Way galaxy. Within Earth, you have the United States of America, the great state of Texas, and Rockwall, my hometown. And so if you're in Rockwall, you are also in the great state of Texas, in the United States of America, on planet Earth, in the Milky Way galaxy. But if you're in Texas, you're not necessarily in Rockwall. Now you could be, but not necessarily. But if you are in Texas, you're definitely in the United States of America, on planet Earth, in the Milky Way galaxy. If you're in the United States of America, you're not necessarily in Texas. But if you're in Texas, you're definitely in the United States of America. And so that's how that subset system works. So let's look at the first example. The first example is 15. What you're trying to do is you're trying to find the smallest subset to which this number belongs. And when you do so, you find that 15 is a natural number. So 15 is like Rockwall. If you're in Rockwall, you're also in Texas, in the United States of America, on planet Earth, in the Milky Way galaxy. So 15 is a natural number, but it's also a whole number, it's an integer, and it's rational. And they're all real numbers because that's all we're talking about in algebra is real numbers. So the next example is Negative 1.4583. Negative 1.4583 is a rational number because I can put it into the form of a fraction. So it is rational, but it's not anything else. It's not natural, it's not whole, and it's not an integer. So it's just rational. It's just rational. And finally, the last example is the square root of 57. The square root of 57 is irrational. If you take your calculator and you go ahead and find the square root of 57, you're going to find a very long decimal that doesn't terminate and it doesn't repeat. And let me give you a hint. Whenever you have a number inside the square root symbol that's not a perfect square, it is going to be irrational. So go ahead and hit pause and do these on your own and find the subset to which these real numbers belong. And here are your examples, or here are the answers. The square root of 9 is 3, so that is a natural whole rational integer. 3 over 10 is rational. Negative 0.45 can be put into the form of a fraction, so that is rational, but it's only rational. And finally, the square root of 12 is irrational. And your last example, we are going to compare real numbers. Here in these situations, you can't compare apples and oranges. You can't compare the square root of 17 with 4 1/3. You need to go ahead and convert them both to decimals so you can go ahead and compare them. But when you have the square root of 17, you can't say, well, that's about 4. That's approximately 4. You need to get a little closer than that. So go ahead and use your calculator and find exactly what the square root of 17 is. And you find it's about 4.1 something something. And you're comparing it against 4 1/3. And so remember, the alligator is going to eat the larger number. And so you would say the square root of 17 is less than 4 1/3. So go ahead and do the on your own. Hit pause. And when you find the square root of 129, you get 11.35 something something. And so then you can tell that the alligator is going to eat 11.52. So you read this as the square root of 129 is less than 11.52. So go ahead and do your homework, memorize your subsets, and let me know if you have any questions.